Thank you very much for the introduction, and thank you for coming. So yes, so let me start with the introducing some incompressible fluid models. So the most famous one would be the Navier-Stokes equation, maybe because of the millennium problems. And yeah, so the equation looks like this, and it describes the motion of incompressible viscous fluid. You can just think of water. So in the equation, it has two unknown functions, u and p, where u represents the flow velocity and p is the pressure. The first equation simply derived from the Newton's second law, F equals to ma, where the force is generated by pressure and internal friction. So here, nu measures the internal friction, and for Navier-Stokes, we assume it is positive. The second equation explains the incompressibility, which explains the volume-preserving property of the fluid along the trajectory. For the domain, I just put the physical domain R3 in space and time, but one can also consider more general setting of periodic or bounded domain, or even n-dimensional space. Yeah. On the other hand, when nu equals to 0, we call this equation as the Euler equation, and it is indeed like no friction case, so it is ideal. But even for this ideal case, we have similar difficulty as the Navier-Stokes. Aside from the Euler and Navier-Stokes, we have surface quadrature-Sophic equation, which is often mentioned as the toy model of 3D Euler and Navier-Stokes because the solution behavior has strong similarity, but the domain is on two-dimensional space. So it seems that it's easier to play with this equation, but even for this toy model, not much, we haven't had a good understanding on solution behavior. So, okay, so we have evolution PDEs, then what's next? The first question one would ask is the well-posedness. The well-posedness consists of three basic questions. Does the solution exist? Is it unique? And the last question is more important in physical or numerical application, which is, does the small change of initial data makes small change of solution? The answer for this question fully depends on solution space. Yeah, so when all the answers are positive in some space X, we say the PDE is well-posed in the space X, but otherwise we say it's ill-posed in the space. Then what are the answers for these questions for the incompressible fluid models? When we work on solution space with sufficient regularity, in other words, when we deal with smooth enough solutions, the well-posedness theories are well established. But in this solution space with low regularity, not much answer had been known. But very recently, several schemes were invented in this direction. So we have had tremendous improvement in the ill-posedness. So let me first summarize the recent results. The recent results are roughly twofold. One is breaking the existence and continuous dependence on initial data at the same time, and the other is breaking the uniqueness. So let's talk about the first case. So as I mentioned, for smooth solution, we have the well-posedness. Then there would be a solution space with the boundary regularity at which we are not sure the well-posedness anymore. So on such spaces, Buguen and Lee prove the ill-posedness of 2D and 3D Euler equation. And I made a little bit of extension by verifying the ill-posedness still holds even for logarithmically regularized 2D Euler equation in the borderlines of a loop space. On the other hand, in the direction of the non-uniqueness, since Camillo and Saicalahidi first adopt the convex integration scheme to the 3D Euler equation, there has been huge progress. And one of the successful points would be the unstaggered conjecture was solved based on this scheme. And also these schemes were further developed and applied to the other fluid models like Navier-Stokes and SQG. So for the remaining time, I'm gonna focus on the non-uniqueness of SQG equation. Interestingly, for this toy model, it was suggested that the convex integration scheme doesn't seem to be amenable. So let's first see the reason why. Before that, let me outline the convex integration scheme for 3D Euler. And here, for simplicity, I assume the periodic boundary condition in space-time. Then 0 is the trivial solution. So here, we're going to construct the non-zero weak solution based on induction scheme. Then at each step, we require the approximate solution satisfies the relaxed equation, which allows the error of the form divergence of a trace-free symmetric matrix. And of course, this error should converge to 0 to make the limit satisfy the original equation. Okay, then now let's assume we have n-step solution. Then how can we find the next step solution? Well, if you see the equation for the perturbation, our main job is make the current error much smaller than previous error. And for that, we definitely need to kill the previous error. And the idea of doing that is using the highly oscillating perturbation as a corrector. So you can think the following simple form. And here, lambda is a very large number, and k is unit vector, and ak has low frequency. So in other words, if you see this perturbation on Fourier side, only the frequency mode, high frequency mode close to lambda will alive. Then what's the benefit of this highly oscillating perturbation? First, since the perturbation has much higher frequency than the previous step solution, it will not cancel out the previous one. So when you send limit, it will not converge to 0. And also, this allows the main error occurs at the level of low frequency term, which consists of two terms. One is the previous error, and the other part comes from the nonlinear term, especially the cross product of two conjugate. Then the situation gets much simple. Now it's just enough to choose AK, which kills to the previous error. But of course, rigorously speaking, it requires the geometric lemma. Then we need to add more waves and so on. But let me omit that part. But this idea doesn't seem to be working for SQG because the nonlinear term of SQG has different structure with that of the Euler. So let me first write the nonlinear term as divergence form, and then this velocity will bring the odd multiplier. Then actually this odd multiplier is problematic because when you plug the highly oscillating perturbation, the leading order of the low frequency part always disappear. So it seems that there's no way to cancel out the previous error. So for this reason, most results were towards like non-odd multiplier case. But recently, Buckmaster and Scholar and Bicol proved non-uniqueness for time-dependent SQG. And the way they overcome the difficulty was by applying the convex integration scheme to the SQG momentum equation, which is equivalent to SQG, but it has a similar structure with 3D Euler. So once you turn to this momentum equation, then the remaining analysis is similar with 3D Euler case, but it requires some heavy technical details. But one interesting part in their proof was the perturbation that they constructed at each step has like the form of the failed answers. So that brought us back to the question again, is it really impossible to apply the convex integration scheme directly to SQG up to some modification? And our answer was no, it is actually possible if we make a little twist. So we wrote the equation, the result for stationary SQG, and here we include my collaborator Chung and Lee. And our main idea was actually pretty simple. We just go down to the next leading order term of the low frequency and use that to cancel out the previous adder. But it, of course, requires a new scheme for the cancellation, but that can be easily done based on some algebraic lemma. Then what's the benefit of this scheme, the direct scheme? Of course, it makes the proof shorten. And also, this scheme is more applicable for similar type equation, like active scalar equation with odd multiplier. Okay, so this is my recent results. Then what's next? Well, there are still many fluid models which are waiting for non-uniqueness results. So I would like to develop this convex integration scheme for those models. Thank you very much for your attention.